your quiz is going to cover 313 and 314. It's only 7 questions, 6, 7 questions, something like that. Obviously, part from 313 and 314. The parts from 313, so like this first page of your quiz review is all 313. This is your polar coordinates. So you have to know how to plot a polar coordinate, find an additional representation, and then convert between polar, rectangular, and polar. So I'll kind of go through a little bit of that. And then the 314 part is all the graphs of polar grids. Polar, all the different types of polar graphs. Minus a spiral. Like I just didn't put a spiral on your quiz, so you can at least eliminate that one from it, okay? The conversion of it, okay? So the first thing you'll need to do is make sure you know how to like plot a point. So if I gave you like 3 pi over 4, and I asked you to plot that point and then find 3 additional polar representations of that point. So I'll give you a grid. It's going to look just like this one here, okay? I'll give you that grid. You'll plot the point, and then you'll have to find 3 additional names of that same point. So let's start with the plotting. I'm going to go to where 3 pi over 4 is, which is over here, and then it's a positive 2, so I literally just go out to the second ring, and I plot a point. If it was a negative 2, I'd go the other direction. Now, in order to find the additional polar representations, and it would say between negative pi over 2 and positive pi over 2, that means that my answer cannot be less than 2 pi, and it can't be bigger than 2 pi. So there's really 2 ways to find this. One is like if you could look at that and visualize your other angles, you're free to do that, okay? I can look at this and say, I know that coordinate point, I can go forward and get a positive angle, but I can also go negative, or I can go clockwise and get a negative angle, and that would be positive 2 for my radius and negative 5 pi over 4. So I could do that. Or you can keep your r and add and subtract 2 pi. One of them is going to be outside your range. Like if I take a positive angle and I add 2 pi to it, it's too big. It's going to be outside your range. So only one of those will work. You'll either be able to add or subtract 2 pi. So in this case, if I took 3 pi over 4 and I subtracted 2 pi, which would be 3 pi over 4 minus 8 pi over 4, I get the negative 5 pi over 4. So if you want like a little cheat sheet of how to find those points and you're not good at like just visualizing it, that's one way to do it. To get the other angles, we'd be using the negative r's. So a negative 2 would be in this quadrant, in my 4th quadrant. So I need it to go the other direction, which means I can do negative 2, 7 pi over 4. Or I can give the negative angle of that 7 pi over 4, which is negative pi over 4. If it doesn't make sense for you to do that visually, then you can change the sign on the r and then add and subtract pi. So out of these, out of adding and subtracting 2 pi or adding and subtracting pi, you will be able to get 3 angles that fall between negative 2 pi and positive 2 pi. Yep. Yeah, because you're going to have to get 3. So the only way to get 3 is 1 r is the same sign as your original, and the other 2 are the opposite signs of your original. So if my original is a negative r, then I'm going to get 1 other negative r and 2 positive r's, like that. But if you just follow that little pattern, either you keep the sign on the r and you positive add or subtract 2 pi, or you change the sign on the r, you add or subtract pi, you'll manage to find all 3. Yeah. So negative 5 pi over 4, like I'm looking for another name of this angle. Positive, it's 3 pi over 4. Negative, it's the one that, like, remember if we fold it like a hamburger? It'd be 5 pi over 4. So those are the same names. Say again? Yep. All right, so that's like 1, 2, and 3, okay? Then 4 says convert polar to rectangular. So I'm going to go from polar to rectangular. And the polar is my r, theta, and the rectangular is my xy. And for these, you just do r cosine theta, comma, r sine theta. And you'll find out what theta is. You'll find the sine and cosine at theta. you'll multiply it times r. So those, obviously, you need to know your unit circle angles for those. Then comes rectangular to polar. So I'm going to start x, y, and I want to answer r theta. And these are the ones that you have to start by figuring out what quadrant they're in. So find the quadrant of the point. Because once you find tan of theta, there's going to be two answers for the inverse of tan theta. And based on where that original one lies is where your answer is going to be. All right, so if I had negative 6, 6 as my xy, then that's in the second quadrant. That means whatever angle I pick for theta has to be in that second quadrant. So then to find theta, I do tan of theta equals y over x, and then I do tan negative 1 of y over x. And then pick the angle. In the quadrant from the beginning. So in this case, I would say tan of theta equals 6 over negative 6. Tan of theta equals negative 1. And I want to tan negative 1, negative 1. So where is tangent negative 1? 3 pi over 4. Also 5 pi over 4. I mean 7 pi over 4. But we said we want the one that's in the third quadrant. So I pick 3 pi over 4. And then r is the square root of x squared plus y squared. So in this case, r would equal square root of negative 6 squared plus 6 squared. 36 plus 36, which is 6 root 2. And then you give that answer in r theta format. 6 root 2, 3 pi over 4. Yep. And the converting of the rectangular, the complex to polar is a lot like that one. So if it's complex to polar, the only difference is how you get the original coordinate point. So it might say something, what did I give you? 6 negative. So what if I said 6 minus 6i? The first thing I would do is put that into rectangular. So what is that in rectangular form? 6 negative 6. What quadrant is that in? It's in the fourth quadrant. So now when I get tan negative 1 of negative 1, I pick the theta in the fourth quadrant. So it's 7 pi over 4. R is still the same. Square root of a squared plus b squared. Still 36 plus 36. So everything else besides that is the same. We would just have picked the other angle. Hello.
Hello, Sarina. Yes, please.
There's only so many tan negative 1s that you have on your unit circle, right? Tan can either only be 0, undefined, root 3 over 3, or 1, or the negative versions of those last three. That's it. Those are the only values of tangent you can have without using a calculator, and you're not using a calculator, so you use your unit circle.
There was a question on the review, and it just had like 7i. Like, how do you know if it's like 0, 7 or 7, 0?
The I is always second.
Oh, okay.
So the I is the B.
Okay.
Good question. Okay, so then comes the fun part. These are the graphs, right? So, oh yeah. Okay, so we're gonna go. So I would put a sheet in between, at the bottom, at the top, wherever you want, but get yourself a fresh sheet. Don't just draw on the quiz review. Okay, we're gonna go through. There are 3 major different types. The fourth would have been the spiral. I did not put spiral on your test. I mean, on your quiz. It might come back on your test, but I did not put on your quiz. There are 3 major different types, and there are 3 graphing questions on your quiz. Okay, so the first, we'll start hopefully easy, and those are the circles. The circles are your r of theta equals a sine of theta, or r of theta equals a cosine theta. There is nothing being multiplied by the theta. There is nothing being added or subtracted. That's how I know it's a circle. Based on your symmetry rules, you should be able to remember which one's which. So if there's sine in my equation, then there's symmetry to the pi over 2 line, which is like your y-axis. Think sine is y, y-axis is pi over 2, okay? If there's a cosine in my equation, then there's symmetry to the polar axis. I have to spell polar right. Polar axis, which is the old x-axis. Same thing. You're going to use that stuff to graph. So it's more as a help than a hindrance. Like if you remember it, it's going to help you graph it. If not, I'm not going to take points off.
So I can't remember it as X or Y.
I mean, you can. But that for you to remember, sure. But if this was an open-ended question and it said what kind of symmetry, you need to put polar or pi over 2. Like it won't be on your quiz, but by test time. Or if it was multiple choice, it won't use x, y. It will use polar or pi over 2. Yep. Okay, so just knowing that, the sine curve has what kind of symmetry? It'd be symmetric to the pi over 2 line, which means your circle is going to be literally on the y-axis, either above the x-axis or below it. I am drawing. It will appear at some point. A positive A puts it above the x-axis. A negative A puts it below the x-axis. Yep.
Okay, well, that's all. That's the same.
Yep.
Do we have to write like dented?
You'll give me this specific dimpled? Yeah. Like you'll tell me which kind it is. Yeah.
Are these multiple choice?
No.
It's on the 8.
Maybe test, there'll be some multiple choice, but for quiz, these are open answers. All right, so the A positive is above, the A negative is below. And what is A's length? Like, what does that represent? A is your diameter. So if you literally know all of that stuff, 0 work is required on these questions. If you don't remember, you blank out, whatever it is, then you could just plot some points. If I plug in 0 on a sine curve, I'm gonna get 0, and I'll know that my circle does not go to the right or to the left. If I plug in pi over 2, I'm either gonna get A or I'm gonna get negative A, and I know it's above or below. So if you forget everything we just went over, you plug in some points. The idea would be that you save time on things like this and effort, because you shouldn't have to. If it's cosine, it falls to the right or the left. Positive A on the right, negative A on the left. And again, same thing. If I know it's cosine, so it's symmetric to the polar axis, that means I can fold it from top to bottom. And I can plug in a point. I would either plug in 0 and get A, or I would plug in 0 and get negative A. I would then be able to figure out what direction it goes. So the circles should be easy, okay? Then we go roses. Yeah.
You just have to go to the top point, and then we can just draw a circle out the rest, right? You
Yep.
don't have to actually individually
Nope.
make sure it's right.
Correct. All right, so I know a rose is a rose because it will have something being multiplied by the theta. So we gave the n as the example in the notes, and the n will be 2, 3, 4, whatever it is, okay? It's going to be, that's how you'll know it's a rose. A is the length of a petal. So the number at the front is the furthest point out. If it was 5, that means the biggest radius you can get is 5. If n is odd, no, then it's the same. Good. Then it equals the number of petals. If it's even, that's when we double.
I watched YouTube videos this week. I just had to be I did.
If it has an even number of petals, then it's also, in addition to the original symmetry, so polar axis and pi over 2 axis, this would also be symmetric to the pole. which means like whatever happens up here happens down here. Whatever happens over here happens over here. So if I know I can find one of those petals, this actually has symmetry to all three. It has polar axis symmetry, pi over 2 symmetry, and symmetry to the pole. The pole is your origin. So like whatever happens here, whatever happens here, happens here. Or if I fold it diagonally on the y equals x or y equals negative x lines, they would also overlap. That's kind of what the pole would be, just like the origin. So for a rose, I would say this is a rose. It has this many petals. The length of the petal is blank. And then I would find my first petal by setting my equation equal to that petal length. So if I had 5 sine 2 theta, then the first thing I would do, well, it would be r of theta equals this. Then the first thing I would do is say it's a rose. It has how many petals? 4 petals. Length of each petal? 5. What kind of symmetry? Pi over 2 and the pole. Or the origin. Okay? Because it's sine.
Wait, but like, even if it's, can it be all 3?
It can be all 3. It guaranteed is this. It could also be all 3. Yep. Okay, so now I would find one petal. And to do that, I'm going to make r my petal length. So I'm going to say 5 equals 5 sine 2 theta. And then I'm going to solve. So I'm going to divide both sides by 5. I'm going to find where one of my petals is.
Then we can like guesstimate the rest.
Where is sine 1? Pi over 2. So pi over 2 would equal 2 theta. Divide by 2, multiply by 1/2, and theta equals pi over 4.
Are we gonna have to do like on the level side? There was a question about setting it like what are the zeros?
I mean, you could, that would again be just additional points. You don't have to. Okay, so I know I have a petal. My theta is pi over 4. My r was 5. So 5 pi over 4 is one of my points, or one of the petals is at pi over 4, which means it looks like this.
So in the case that I was saying, you had to like find it to the left and the right of each line, or each one of the main lines.
Well, you could just set it equal to 0. Is that what you mean?
Because like what it did is like I said it equal to 0.
Yeah.
And you get 2 points.
Then they both have 0, 0. So
And then
just like that, it goes out, comes back in, goes out, comes back in. Every time it comes back in, it's got another 0.
Yeah. So then after I got the 2 points, like we need
Oh, you needed to keep finding them because it was a multiple angle.
to find it to the left. And the
Right, because you're adjusting your interval as well as your answers. Yeah. All right, then I know this has access to the symmetry to the pi over 2, right? So that means that at pi over 4, there's also another petal. At 3 pi over 4, sorry, which would be there. And then because whatever happens in the top right quadrant happens in the bottom left quadrant, I know it happens at 5 pi over 4. And whatever happens in the top left quadrant happens in the bottom right quadrant. I know the other one is at 7 pi over 4. Now let's pretend you didn't know any of that stuff. How could you find these things? Plug in a point. If I plug in 0, I'm going to get 0. If I plug in pi over 2, I'm going to get 0. If I plug in pi, I'm going to get 0. And if I plug in 3 pi over 2, I'm going to get 0. And it helps you almost none, except to know that my petals are not there. So you're going to plug in points. You could plug in pi over 6, pi over 4, pi over 3. And you don't have to go until you find every petal. Like if I plug in pi over 6 and I know my radius is somewhere small, and then I do pi over 4 and I find my radius, I don't need this one. I know the overall shape. So it doesn't have to be perfect, okay? I'm not telling you you have to find every time r is 4 or 5, whatever this was. It's just that if you do find at least one, it should help you find the others. Yep.
So like find where like one of the petals is, you just say equal to the length.
Yep. And you could set it equal to the negative length and find where the other petal is. Like you could do it that way. Or you could plug in points. If you have no idea, then you're plugging in points. And because this has symmetry to the pi over 2 axis, whatever I plug in from the right side of my graph has to flip over to the left side of my graph. So I wouldn't even plug in points over here. I would plug stuff in on this side, and then I would flip it to that side. If it was cosine, I would plug in points from the top and flip them down to the bottom. Don't waste your time plugging in duplicate points.
So you just found power before and reflected it.
Yep. If it was not symmetric to the pole, like let's say it was cosine, it could be something that's like this guy. That's not going to have the same kind of symmetry, right? Like this, you might have a pedal here, and then you could have a pedal here and here. So it just depends. The only time it's both is if it's an even amount of pedals. Yeah.
You're gonna give us the graph, right?
Yes. Yeah.
I was working.
Yeah, no, it's the exact same one that's on your quiz review.
So like, but if
Actually, I think it has pi over 12, but it's similar.
if it were to ask us to graph something like that, how would we know where
I would plug in points. So I would find this pedal. It's going to give me that pedal. I know there's 2 other pedals. So I'd plug in something from this quadrant, see where it goes. And then if it's polar axis, then I just reflect it.
What if there's like 7?
There won't be 7 pedals, but you could just keep finding points. I mean, in the world of polar functions, could there be 7 pedals? Sure. Do I want to watch you guys cry tomorrow during your quiz? No, there will not be 7. And the last example I gave 12 pedals. I'm like, you're not going to get one with 12 pedals. If it was multiple choice and one of your things was 6 theta and one of your answers had 6 pedals and one had 12 pedals, I'd expect you to be able to tell that one, but not draw it from hand. Yep.
I was gonna say, is the amount of poles that you have the amount of zeros that you're gonna have?
1. Well, because 1 produces 2 zeros. Yeah. Yeah. Yeah, because it starts, but 1 0 technically starts and stops each pedal. So yes, same zeros as pedals. But you might not be able to find them all unless you alter your interval. So don't stress out about that. Plug in some points. Yeah. All right, so then the last one is the limison. This is the one that's going to require the most amount of work. Okay? Because they're not as easy. You can't just find a pedal, okay? If there's an inner loop, you got to find the inner loop. If there's a cardioid one, you got to find the cardioid one, okay? So try to visualize that slide that we did, right? The very far left one had the smallest a over b, and then work your way backwards. That's how I try to remember it. These are r of theta equals a plus b cosine theta, or r of theta equals a plus b sine theta. And it could be plus or minus, but we ignore the plus or minus when we're figuring out what kind they are. So as soon as you see adding and subtracting, you know it's a limison. And then the furthest one to the left, what was that furthest one? It's the inner loop, and it's the less than. It's the smallest value. So if a over b is less than 1, then I have an inner loop.
You know the names?
Yep. And the inner loop goes something like that, or this is awful drawing, but something like that. Like a pretzel-ish. Yeah. So think about your symmetry, right? If it's the top one, what kind of symmetry does that have? It's the polar axis, which is cosine. So this is a cosine graph. It could either face the right or the left, but at least you know that the loop happens on the x-axis or on the polar axis. If it's in the bottom and your little knot or loop is happening at the top or the bottom, now it's sine.
Cosine is left and right.
Correct. Okay, what came next? The cardioid, official term, the one that looks like a butt. Okay, in between what 2 values? No, sorry, equal to what value? Equal to 1. And if you think about the same concept, so the little heart shape will either happen on the right or at the top or at the bottom or the left. Polar axis, this is still cosine. Pi over 2, this is still sine. Again, it could be top or bottom, right or left. Yeah. Then came, oh, this is cardioid. Cardioid. Then came in between 1, nope, not equal to, in between 1 and 2, and this is dimpled. Yep, think about it. Like if I kept pushing from the inner loop out, it gets a little point first, then it would soften, and that's your dimpled limison. Looks like a kidney bean.
That's if it's
In between 1 and 2.
Can we just write dimpled?
You can write dimpled. I didn't even like give a specific line for it this time. Like on your test, it might be worth part of the points. Let me make. What I would say is that if your graph is wrong, but you gave me partial of the other stuff, like if you could give me the name of the graph, the symmetry of the graph, that kind of stuff, I'll throw some points in your direction if your graph is wrong. But if your graph is wrong and then there's no work to back any of that stuff or no other knowledge about it, then I can't help you. Okay, and then the last one. If it was pushed all the way out. Greater than or equal to, thank you. It's called
greater than or equal to.
Oh, convex.
convex, good. And it's like it got pushed up against the wall, it's flattened. Doing a bang up job with these drawings today. And again, cosine, sine. So it flattens. Like you see this, like keep pushing this out. Keep pushing it out, it would flatten it out. Like you took a ball of Play-Doh and slammed it against the wall.
The sign flattens
At the top or the bottom.
Like that, you don't do this one that's like directly in the center.
Remember they used to feed her
What do you mean? Has to be directly in the center.
Why can't it just be on that? It's like the rest of them. Oh, the rest of them are directly in the center?
Yeah, they're all in the center.
bad cases.
They're all on the axis.
Yeah, but the beans. It was the thing with the beans. It's like
All right. The other thing that's helpful is to know that the biggest value for R is going to be your A plus your B. So A plus B equals the biggest R. This is going to be the furthest point. So if I find A plus B, that's my maximum point. If that happens on the x-axis, then I know it's going to be like over here. If it happens on the y-axis, I know it's there. And then I know my loop is opposite it, or I know my heart is opposite it. Does that make sense? The biggest point is opposite your loop or your point or your flattened edge or your dimple. Okay, it's in the other direction, whether that's up, down, right, left, whatever it is. So these are going to require the most amount of work because especially if it's like an inner loop, you have to be able to establish that loop shape. So I would say you're going to find what kind it is, the limison, then you're going to say, okay, I know it's dimpled, I know it's cardioid, whatever it is. I know it has this type of symmetry. And if it has cosine, if it's cosine so it has symmetry to the polar axis, you're going to plug in points from the top of your graph. So I would say maybe go from 0 to pi and plug in as many points as you need to establish the curve. If I do cosine and my loop happens over here, I already get a couple points and I know the loop is happening over here, then I really only need to find the A plus B over here. I don't need all these additional points. If it's a sine and I find the loop at the top, because the cosine would then reflect under here. I would take any point that's above and I would reflect it over. If it's sine, then I'm going to take the stuff from the right-hand side of my graph. And then I'm going to duplicate it over to the left. And again, if it's sine and I get the loop at the bottom or I get the heart at the top or the bottom, wherever it is, then maybe I don't need as many points in the other quadrant because I know it rounds out. But I would say you want to stick to your quadrant points. You want to stick to your over 6s, your over 4s, your over 3s, that kind of stuff. Just make it easier on yourself. Yep.
So like you find the graph at white points
You're plugging in for theta. So like if I had, give me some numbers. Give me a number between 0 and 5. What? 3. Give me a number between 0 and 5. Give me cosine or sine. What kind of graph is this? A limison? Specifically? An inner loop. Why would you do that to yourself? You made an inner loop. Okay. With what kind of symmetry? With me so far? Yes? Okay, so if it's symmetry to the pi over 2, I'm going to pick points from the right-hand side of my graph. Let's start at 0. I'm going to plug in 0. And where am I plugging that into? The r or the theta? Well, there should be a theta there, but you're plugging in for theta. These are angles, so we're plugging in for theta. So if I plug in for theta, let's start at 0. I would get 3 plus 4 times sine of 0. What's the sine of 0? 0, right? The y at 0 is 0, so this is 3. Then I go to the next point. So let's plug in. Let's just do pi. Let's keep going with what we were doing before. Pi over 6. What's the sine at pi over 6? 1/2. That's 5. Then I plug in pi over 3. 3 plus 4 sine pi over 3. What's the sine at pi over 3? Root 3 over 2. Remember, we approximate, so this would be 2. Root 3, that's going to be beneficial to you. Root 3, we say, is 1.7. Root 2, we say, is 1.4. So this would be 3 plus 2 times 1.7. 3 plus 3.4, 6.4. Now, we still haven't hit our biggest point, which would be the a plus the b, which is 7. But we are getting bigger, yes? So where do you think that big point is going to be? At pi over 2, which means this loop is happening where? At 3 pi over 2, opposite the biggest point. Does that make sense? Okay. So if my biggest point, if my rounded part is at the top, then that means my loop has to happen opposite it, which would be at the bottom. Yeah.
Could I get away with just like graphing pi over 4 instead of pi over
Sure.
3?
I would say the better you know where that loop is, then the better it would be to eliminate points. Like if you know that loop's on the bottom, then I don't even need pi over 4. I can go from 0 to pi over 2. Does that make sense?
Could you just add them first, figure out where your highest point is, just do opposite, and
Sure.
find the points for the inner loop?
Sure. So this would be 3. Now we're at sine pi over 2. Sine at pi over 2 is 1. And there's the biggest point is at the top. So pi over 2 gives me 7.
So then you graph it.
So I can start already. At 0, I got 3. At pi over 6, I get 5. At pi over 3, I get 6.4. And at pi over 2, I get 7. And it has symmetry to the pi over 2 line because it's sine. So that this point at pi over 3 is going to happen over here at 2 pi over 3. The point at pi over 6 is going to happen over here at 5 pi over 6. And the point at 0 is going to happen over here. That's not 3. I didn't go up far enough. Sorry. Here. So I already know that this is the top part of my graph. Now I have to find the loop points at the bottom. So I will plug in 11 pi over 6. And I get 3 plus 4 sine 11 pi over 6. What's the sine at 11 pi over 6? Negative a half, right? So it'd be 3 minus 2, which is 1. And then I can do, I could jump, I could do 7 pi over 4. I could jump to 5 pi over 3. Really, you're picking whatever makes the most sense. 4 sine 5 pi over 3. The sine at 5 pi over 3, negative root 3 over 2. This is 3 minus 2 root 3. 3 minus 2 times 1.7.
You skipped over 4.
Yep. I typically either I'm going to do over 6 and over 3 or over 4. I don't do both. So this is negative 0.4. So already I know my point is going here, and then it comes into here. Then I would go 3 pi over 2. And the sign there is negative 1. And now that coordinate point is above the x-axis. And that's how the loop happens. So if I were to reflect this point over here and this point over here, you're going to get the other half of that loop. Bye, guys.